This is the presentation on the TIDE, steel monocoque interdisciplinary digital workflow and parametric structural analysis. The TIDE is part of a much larger master plan project encompassing the Greenwich Peninsula, with a key focus to achieve connectivity between the various components that have been developed on the peninsula over its recent history, achieving seamless connection between transport links, leisure, restaurant facilities concentrated around the O2 Arena. The River Thames surrounding the peninsula, as well as the local residents, enables the peninsula to be enjoyed by all. This leads to the vision of a 5-kilometre link connecting together the various parts of the peninsula, with the TIDE being the first phase. The TIDE is located in an area that is particularly dense with existing structures. The North Greenwich London Underground station directly below, existing ventilation shaft structures, and a car park serving the adjoining residential towers. DS+R architects envisioned a scheme to lift the user experience up off the ground, away from the congested ground floor, providing an elevated highway with the essence in mind to enable users of all mobility to have access to the walkway and to enjoy the unique viewpoints. The core of the project was to enable a full user experience for all users to interact with the surrounding landscape, and therefore enhancements to the ground level through intensive landscaping was also key. The structure is formed from a simple concept of island clusters, connected together by link bridges, continuously joined together forming a walkway of approximately 300 meters. There are 7 clusters formed of between 3 to 8 islands, and a total of 29 uniquely shaped islands, each serving a purpose to provide space and to accentuate key viewpoints along the walkway. The form of the link bridges was based on the principle of honest architecture. The geometrical form of the links corresponded directly to the associated bending moment profile of a link, effectively a simply supported beam with the largest moment at midspan. A total of 8 links connect the island clusters. Though varying significantly in length between 5 and 23 meters, the links are designed as simply supported elements sat on elastomeric bearings at either end. This enabled the decoupling at island connections and to allow for free movement under thermal loading. Steel was the natural choice of construction due to the significant benefits, including suitable construction to achieve complex interfaces with surrounding existing structures, manageable loads for fabrication, transportation, and installation, the high levels of accuracy that could be achieved with fabricated steel elements, consistency of high quality finish demanded by the project, and also reduced site construction and installation time, as the majority of time is associated with shop fabrication off-site. It was clear during the early stages of design that adopting a lightweight steel solution would bring challenges regarding dynamic behavior. The links are susceptible to dynamic excitation due to the following: its lightweight construction, limited surface finishes, long spans, and fully welded construction. Time history analysis was utilized in digital analysis models. However, it was key to understand and to define these serviceability design criteria. No response factor is strictly codified, therefore readily available publications on dynamic response was used to advise the client. A response factor of 70 was agreed. This is considered to be on the conservative end of the median comfort range for footbridges based on these published documents. Computational design tools enabled us to extensively assess the dynamic performance of the structure under a range of forcing functions based on single pedestrian, a group of joggers, and crowd loading. Using analysis models, we were able to review particularly sensitive structural elements in further detail to resolve any dynamic excitation issues. Tuned mass dampers were considered to be a cost-effective solution to dynamically sensitive links. They are simple in construction, with a mass connected to springs and damping elements. The interaction of the TMD would enable significant reduction in the vibration response, and this was studied in depth using computational analysis models. Computational and parametric tools developed by AKT together with DS+R architects allowed a system of iteration to be produced, where structural requirements could be maintained, for example, stiffener number and locations based on plate geometries. This allowed the architecture team to quickly study the varying forms throughout the project and to make adjustments by refining a set of parameters. This included platform area, the shape, the flare, but also tree base and depths. Computational tools were relied upon heavily during the design and structural analysis of the islands and links. The parametric model was an essential tool both to streamline the iteration process and to enable changes to be quickly and efficiently reviewed, as analysis models could be automatically generated. This allowed for quick feedback to inform global behavior in terms of stability, to minimize forces into foundations, but also to inform changes and/or opportunities in plate thicknesses, stiffener locations, and numbers. This was particularly useful during the detailed design stages. In the latter stages of detailed design, local detailed design models could be produced from the parametric models. For example, column-based connections were key to understand any strength enhancing requirements, such that additional stiffness could be introduced to deal with local stress peaks. The drawing production process was streamlined through the use of AKT developed interoperable tools between platforms. Baked geometry within Rhino was transferred into Revit conceptual mass, then into Revit project environment so that construction drawings could be produced. This included all the general arrangement drawings, planned sections produced from the Revit model. Once the main fabricator, a steel specialist from Italy, Cimolai, was appointed, the model was shared to enable the contractors to tackle the complex geometry and to produce detailed fabrication drawings required for their processes. The parametric model was an invaluable tool to allow detailed coordination and collaboration for finer structural details and to achieve seamless, non-visible construction joints required by design. Physical mock-ups were part of the fabricator brief, and the models allow for focused mock-ups to be developed in 3D prior to fabrication. This was an extremely useful process to figure out the vastly complex interfaces between all the different trades. Due to the size and weight of these elements, installation and erection had to be carefully planned and thought out. The models allowed the fabricator to produce safe installation sequences with minimal temporary works, which were tested in Italy prior to being shipped to London. To enable the realization of the architecture and the honest structural form, a steel shell structure was the natural solution to adopt. Interdisciplinary approach throughout the journey from concept to construction was key to its success. Computational tools developed between structure and architecture was a key achievement to deliver a streamlined design process. Sharing the model with the fabricator enabled opportunities to be taken whilst also highlighting any potential issues before fabrication. The delivery of the project was a fantastic success, achieved by all through hard work, dedication, and we would like to give special thanks to the client, Night Dragon, the architecture team, Dilla Scafidio and Renfro, Neiheiser Argyros architects, and the specialist fabricator Cimolai. Also the design consultants who provided their technical excellence and the structures team at AKT II.